Glorious. Unacademy Combat. Compete, crack, conquer.
A challenging gate contest engineered to give you an experience like none other.
where you put your knowledge to test.
and battle it out with a test.
To bring out the best in you, Unacademy Combat is the most competitive, gamified contest for gate till date, with the best of the questions by best educators.
With detailed video solutions from top educators right after each contest.
Combat live with peers to get real-time rankings and win big.
Participate in every contest to improve your ratings.
Challenging contests every fortnight or alternate Sunday. Live ranking after every question. Big rewards for top rankers. Your passion to crack gate deserves this. Your hard work towards your dream deserves this. Fuel your inner fire for the ultimate gate challenge. Unacademy Combat. Register now.
Hi, hello, good evening all. Welcome to Unacademy. This is Banu Prakash, expert in GATE and ESE. I did MTech from NIT Kurukshetra. I have 10 plus years of teaching experience and I trained many students throughout our country for different competitive exams like GATE, ESE and PSUs. I expertise in the subjects of electrical machines and power electronics. BPC10 is my referral code. Use this code. You will get 10% to discount on Plus subscription as well as Iconic subscription. let us know about what are the benefits of the Plus and Iconic subscription initially. So by taking Plus subscription, you can get live classes from the top educators of the country. So that means here we have a many teachers per each subject, so that you can select the teacher as per your choice. And second one, here we can get structural schedule per 3 months, 6 months, 12 months and the 24 months. Okay, and also you can get unlimited practice questions and test series. So by you writing the test series, you can analyze your performance day by day, so that you can improve where you are weak in that particular area. And by another subscription, that is Iconic subscription. So by taking Iconic subscription, you can get all these 4 benefits. In addition to these, you will get some extra benefits. One is a personal coach. Personal coach means it is a one-to-one guidance for your preparation, okay, for your preparation of the GATE and ESE. And also you will get proper study planners, that means how to prepare for GATE effectively, similarly how to prepare for ESE effectively, and if you want to prepare for any AEs, okay, so that you can get all proper study planners. And another one is a expert guidance, ESE mains questions and answers. So these are the benefits of the Plus and Iconic subscription. So here, if you want to take subscription, use my code BPC10. It is my referral code. You will get, by using this code, you will get 10% to discount on Plus subscription as well as Iconic subscription. Okay, and next one, what about the price for the Plus and Iconic subscription? So by taking Plus subscription, this Plus subscription is available for 12 months, 18 months and 24 months. Okay, for 12 months fee is 27,225 rupees. Okay, and for 18 months fee is 34,650 rupees. For 24 months fee is 39,600 rupees. Okay, and Iconic subscription is available for 12 months and 24 months. For 12 months fee is 45,225 rupees. For 24 months fee is of 66,600 rupees. How to install Unacademy learning app? Just do one thing and open your Google Play Stores or any that is a Play Stores, and search about Unacademy learning app, and after that install this Unacademy learning app in your phone. Then after, the access pre-special classes taken by the top educators. So if any code is asking to access the pre-special classes, use my code, that is BPC10. It is also the referral code and invitation code to access the pre-special classes. And this is the Unacademy GATE English January month schedule. Communication system 9 to 10 a.m. Engineering mathematics 10 a.m. to 11 a.m. and analog electronics 4 p.m. to 5 p.m. Engineering mathematics from the 5 to 6 p.m. and aptitude 6 p.m. to 6:15 to 7:15 p.m. and measurements for Genco, Transco, Discoms, SSC, AE at 7:30 p.m. to 8:30 p.m. and electrical machines for Genco, Transco, Discoms, SSC, JE, RRB, JE at 8:30 p.m. to 9:30 p.m. This is the January month schedule of Unacademy GATE English channels. Okay, so in previous class we had discussed about how to derive the EMF equation of the transformer and what are the conclusions from the EMF equation of transformer, and also we had discussed about what are the possible questions from the EMF equation of the transformer. So we know that EMF induced in the primary winding of the transformer, E1 is equal to 4.44 okay, phi maximum Fn1. So this is the EMF induced in the primary winding of transformer. And similarly, EMF induced in the secondary winding of the transformer. So that is equal to 4.44 phi maximum Fn2. So EMF equation in the secondary winding of the transformers. And what are the conclusions we can make from this EMF equation? So we know that first conclusion 1, okay, this conclusion 1 is the magnetizing current of the transformer lags the applied voltage V1 by the 90 degrees, okay. And second one is a magnetizing current and flux of transformer, flux of transformer are in phase with each others. Got it? Flux of transformer are in phase with each other. And third one is a EMF induced in the primary winding of the transformer. The E1 lags pi 1 by 90 degrees. Okay, flux in the primary winding of the transformer. And third conclusions, the fourth one is a EMF induced in the secondary winding of the transformer also the lags the flux by the 90 degrees. Okay, these are the conclusions the obtained from the EMF equation of the transformers. Okay, and also what are the observations from the EMF equation of the transformers? So we have discussed that is the first one EMF equation of the transformer in terms of the flux density and net cross sectional area of the transformer core. So that one we can write like this: E1 is equal to 4.44 B maximum AN Fn1. Okay. Similarly, EMF induced in the secondary winding E2 is equal to 4.44 B maximum AN Fn21. And the second observation, that is the EMF per turns ratio in the primary winding is equal to EMF per turns ratio in secondary winding of the transformer. So that means E1 divided by N1 is equal to the E2 divided by N2. So that equal to 4.44 B maximum ANF. So this is the EMF per turns ratio is constant from the primary winding to secondary winding of transformers. Okay, and third one we had discussed, third observation. So that is here the transformation ratio. So the transformation ratio K is equal to, it is the ratio of number of turns from the secondary winding to primary winding of the transformer, that equal to K equal to N2 by N1, that equal to E2 by E1. So it is a transformation ratio. Suppose if we want to calculate turns ratio, how do we calculate the reciprocal of the transformation ratio? Is known as a turns ratio of the transformer, where turns ratio is denoted by small a. Okay, this the where K is a transformation ratio. And fourth observation, already we had discussed all these in the previous session. The fourth observation is the size, the relation between the size of the transformer and frequency of the transformer. So always the size of the transformer is directly proportional to, inversely proportional to the frequency of the transformers. Got it? And fifth one, relation between the kVA rating of transformer and frequency of the transformer. So always kVA rating of the transformer or MVA rating of the transformer directly proportional to the frequency of the transformer. And another observations from the EMF equation, so that is a relation between the flux density and V1 by F ratio. So that means during operation of the transformer, so that is a B maximum directly proportional to V1 by F ratio. Okay, maximum flux density of the transformer is a directly proportional to V1 by F ratio, where V1 is a applied voltage and F is a frequency of the transformers. Okay. Good evening all. Bharat, good evening. How are you? So this is the discussions in the previous class. So today we will discuss about some interesting questions based on this concept. Okay, it is a one of the question. If transformer is operated by keeping applied voltage constant and frequency is reduced to below its rated value, then magnetizing current of the transformer would be. Okay, can you answer this question? All of you, please read the question initially, then try to answer this question. Yes, good evening Revati, good evening all. Okay, I will give you 30 seconds. Answer this question, all of you. Okay, so listen. So by keeping applied voltage constant, applied voltage is a constant and frequency of the transformer is reduced to below its rated value, then what is the magnetizing current? So already I have mentioned that what is mean by magnetizing current. The current required from the source to create flux in the transformer is called magnetizing current. So let us apply the given quantities in the question. So what was given here? The one is a by keeping applied voltage. If the applied voltage of the transformer V1 is a constant, okay, it is a some finite value, and frequency of the transformer reduces, okay, the below its rated value. Okay, it is reduced to below its rated value. For example, if the transformer is designed at a frequency of the 50 Hz, so instead of the 50 Hz, it is operated less than the 50 Hz, but voltage remains same. At this condition, how much amount of the magnetizing current, whether it is increase or decrease or remain same or either increase or decrease. Okay, this is our question. So already I mentioned that. So first tell me, is this question belongs to designing side or operating side? Anyone? Is this question belongs to designing side of the transformer or operating side of the transformer? Designing side or operating side of the transformer? Operating side. Very good. That's correct. So what is the condition to be applied during the operation? So we know we know this condition. So during operation of the transformer, okay, so maximum flux density of the transformer directly proportional to V1 by F ratio. Got it? So here given that here applied voltage is a constant. Got it? And frequency of the transformer is reduced to below its rated value. So by keeping applied voltage constant, frequency is reduced, then maximum flux density of the core will be increased. So therefore maximum B maximum will be increased, okay, due to this condition. So then what will happen? As a here, in order to increase the B maximum, so in this condition, so we know do here B maximum is equal to phi maximum by net cross sectional area of the transformer core. So during operation, area is a fixed at the time of the designing. So that during operation of the transformer, so here B maximum directly proportional to pi maximum values. Okay. So in order to increase the flux density in the transformer core, so to increase B maximum flux density, so phi maximum should be increased. Right? So this is a should be increased. So here phi maximum should be increased to increase the maximum flux density. Then how do we increase the phi maximum? So we know that flux is equal to mmf by, so here number of turns multiplied by magnetizing current, so divided by the reluctance of the core. So here to increase the flux, then what will happen here? So in this case, so let us draw here a magnetization curve. So magnetization curve drawn between the flux and magnetizing current of the transformers. Got it point? So initially, if the magnetizing current is equal to 0, the flux is also equal to 0. Neglect residual flux. So then what will happen? As magnetizing current increases, flux is also increases linearly until saturation of the magnetic core. So behind that, then what will happen? As a magnetizing current increases, there is no change in the flux. Okay, this is the increment in the flux in the saturation region. So now it is a magnetizing current, the one. So just above any electrical machine is operated just above the saturation point. So this is the saturation point, right? So now this point is the saturation. So any electrical machine operated just above the saturation point. So to get advantages of the linear characteristics, and at this condition, how much amount of the current here, how much amount of the current required to create the flux here? So for example, phi 1. So now here is this magnetizing current I nu 1. So now here, if we want to increase the flux very high value, so then what will happen? It goes to, that means the transformer goes into the deep saturation, so which demands high magnetizing current. Okay, so to increase flux in saturation region. Okay, this is the operating point 1. Okay, initially it is operated at rated voltage condition. So in order, if the transformer is operated less than the rated value, the transformer core goes into the deep saturation here. In order to increase the flux in the saturation region, the transformer core goes into deep saturation. Deep means very large amount of the magnetizing, deep saturation, which demands high magnetizing current. So got it point? So therefore, what is the answer here? Magnetizing current of the transformer increases very large amount. Very good. So Satish, you have given option A. Venkat, you also given option A. That's correct. Revati, you have given option C. That's not correct, Revati. I think just correct it. Option A is a correct. Okay, is that clear, everyone? So next, let us solve one more question. Same concept. I think it is the same question, right? So if transformer is operated by keeping frequency constant and voltage is reduced to below its rated value, then magnetizing current of the transformer would be. First, whenever question comes, this type of question comes in the exam, first to divide the question whether this question belongs to designing side or operating side. So if you know this concept, if you know this simple technique, you can answer any type of question. First to tell me, is this question belongs to designing side of the transformer or operating side of the transformer? Okay, here given applied voltage is reduced, applied voltage V1 is less than the V rated value, right? And frequency of the transformer is constant, that means it is equal to the rated value only. Okay, frequency is constant. So during operation of the transformer, during operation of transformer, what is the condition? B maximum directly proportional to V1 by F ratio. By keeping up frequency constant, okay, applied voltage is a reduce. Then what will happen? Flux density of the transformer is reduced. B maximum will be reduced. So here decreased in the flux density decreases the requirement of the flux. Okay, and decreased in the flux decreases the magnetizing component of the current of the transformers. Okay, what is the answer for this question? Option B is a correct. Very good. Okay, next. So we have a one question like this. Which transformer is small in size? Okay, options are given. Option A 100 kVA 50 Hz. Option B 100 kVA 60 Hz. And option C 100 kVA 40 Hz. And option D 100 kVA 30 Hz. Okay, now tell me which transformer is small in size? Already I mentioned that size of the transformer is, so we know the relation, size of transformer is inversely proportional to frequency of the transformer. Okay, the transformer which has high frequency is less in size. First read the question, Venkat. Here size of the transformer is inversely proportional, right? Suppose the transformer which has high frequency is small in size. Okay, what is the answer? So option B is a correct. Very good. So next one. So let us solve this question. If transformer is operated by reducing voltage along with frequency such that V by F ratio constant, then magnetizing current of the transformer would be option A increased, option B decreased, option C remain same, option D either increased or decreased. What is the answer? Okay, how do we answer? This question also belongs to operating side of the transformer. So we know that during operation of the transformer, maximum flux density of the transformer directly proportional to B maximum directly proportional to the V1 by F ratio. So here given that reducing the voltage along with the frequency such that V by F ratio constant. Okay, as V by F ratio constant, so what will happen? Okay, this B maximum will be constant. So that means as V1 by F ratio constant, so the change in the flux density remains same. Okay, and there is no change in the flux density in the transformer. The maximum flux of the transformer also remains same. So if there is no change in the flux in a transformer, so we know that flux is equal to number of the turns multiplied by magnetizing current divided by reluctance. So these are the finite value. Only flux is direct during the operation. During operation here, okay, during operation, the flux is a directly proportional to the magnetizing current. So that here there is no increment in the flux. So there is no here the increment in the magnetizing or decrement in the magnetizing current. So that magnetizing current of the transformer remains same. Very good. Option C is a correct. Okay. So now let us solve this question, all of you. A single phase 50 Hz 400 upon 200 volts transformer has flux density of, okay, this is as flux density of 1.6 Tesla when excited with rated high voltage and rated frequency. If same transformer is operated with reduced voltage of 300 volts at a frequency of the 40 Hz, then the value of the flux density would be in Tesla. Or Webers per meter square. Okay, how do we answer this question? So first one, the given transformer is a 400 upon 200 volts. Okay, 50 Hz transformer. So which has a flux density P maximum 1 is equal to 1.6 Tesla, right? And this is a supply is given to the rated high voltage side. So here high voltage is the 400 volts, low voltage is the 200 volts. So this side supply is given. Okay, if it is supply is given here, so what it means, V11 is equal to 400 and frequency F1 is equal to the 50 Hz. This is at case 1. and if the same transformer is operated with the reduced voltage of the 300 volts, okay, at a frequency of the 40 hertz, then the new value of the flux density be maximum 2. Okay, this is our question. So how do we answer this one? First, to tell me, is this question belongs to designing side or operating side? First, to divide the question, then we can answer easily. Is this question belongs to operating side or designing side of the transformer? Operating side. Very good. So during operation of the transformer, okay, maximum flux density directly proportional to V1 by F ratio. So this one is equation. You can write B maximum 2 is equal to B maximum 1 into here V1 directly proportional V1 2 divided by V1 1. So multiplied by F1 inversely proportional. That's why we can write F1 by F2. Okay, this equation is enough to answer this question. Okay, now substitute here where B maximum 2 is equal to, okay, B maximum 1. What is the value of B maximum 1? 1.6 Tesla, right? Multiplied by, and what is the applied voltage in the case 1? First case, this one is the case in the first case 1, and in the second case, okay, case 2, here if the transformer is operated with a reduced voltage of the 300 volts 40 hertz, then what is the value of the flux density? So what is the applied voltage in the case 2? That is equal to 300 volts, okay, 300, and divided by applied voltage in the case 1. So applied voltage here, rated high voltage, so that equal to 400 volts, right? Multiplied by, and frequency of the transformer. Initially, case 1 here frequency is a 50 hertz and the frequency is a 40 hertz frequency. So now simplify this, you will get B maximum 2. It is not 7.5 Revati. Just once again calculate by using the calculator or by using, you can write down correctly also. Is it 7.5? I am also calculating. Let's verify, is it 7.5 or not? 3 and 3 divided by 4. Okay. Yes, that's correct. 1.5 Tesla. Not 7.5. It is a 1.5 Tesla. Very good. This is the correct answer. Okay. So now let us solve one more question. A single phase 50 Hz 400 upon 200 volts transformer has flux density of 1.6 Tesla. When excited with rated low voltage and frequency and rated frequency, If same transformer is operated with reduced voltage of 160 volts at a frequency of 40 Hz, then the new value of the flux density would be. Okay, try to solve yourself first. What we have to do here? This is the same. This question also belongs to during operation of the transformer. So given data is a 400 upon 200 volts transformer. The rated frequency is the 50 Hz. So at this condition, the flux density B maximum 1 is equal to 1.6 Tesla. And when transformer is operated at what condition? Rated high voltage, so that the supply rated low voltage supply is given to the low side of the transformer, low voltage side. And if the same transformer is operated with a 160 volts and 40 Hz the frequency, then what is the value of the B maximum 2? Okay, this is. So how do we answer this question? So during operation of the transformer, maximum flux density directly proportional to V1 by F ratio. Got it, my point? So from this equation, you can write the B maximum 2 is equal to B maximum 1 the multiplied by V12 divided by V11. So into F1 by F2. Okay, we can write actually B maximum 2 by B maximum 1. So directly proportional, that's why it is the V here, second case divided by first case. It is inversely proportional, that's why first case divided by the second case. Okay, so now substitute here B maximum 2 is equal to 1.6. What is the applied voltage in the case 2? So it is a 160 volts. Okay, divided by the applied voltage in the case 1. So that is a 200 volts. Okay, frequency F1 is a 50 Hz divided by 40 Hz. So here the voltage 50 cancelled out. So now it is a 1.6 Tesla. So that what is the answer? 4 by 5 and 5 by 4. Okay. So B maximum 2 is also 1.6 Tesla only. Okay, that's correct. Yes, Venkatesh, you have given correct answer. Revati also got 1.6. Very good. Keep it up. That's correct answers. And Arish, check your answer once again where you did mistake. Okay, and answer this question. It is also one more question based on this concept. A 100 upon 400 volts 50 Hz transformer is to be excited at 40 Hz from 100 volt side. For exciting current to be same. Exciting current to be same means magnetizing. Exciting current means a sum of, okay, this exciting current is nothing but exciting current is a sum of the magnetizing current plus iron loss component of the current. So as exciting current is the same means the given in the question itself magnetizing current is constant. Okay, as magnetizing current constant, then what will happen? The flux is a remain same. Okay, as flux is constant, okay, and maximum flux density of the transformer remains same. Okay, and during operation, okay, as a B maximum is constant means as B maximum is constant, so V1 by F ratio is constant. F ratio is a constant one. So therefore we can write V11 divided by F1 that is equal to V12 divided by F2 values. So initially it is operated 100 voltage side at a rated voltage of 50 Hz and 100 volt side. So now if it is excited with the 40 Hz instead of the 50 Hz, then what is the voltage here? So that this is equal to 100 divided by 50 Hz. Okay, 100 divided by the 50 Hz is equal to, so we don't know what is the voltage, V12, okay, divided by 40 Hz frequency. So now simplify here, applied voltage is equal to 2 multiplied by 40, so it is equal to 80 volts. So answer for this question, option B. Okay, have we got it? Any doubts? Do you have any doubt? We can ask. Okay, now answer this question. A 20-turn iron core transformer is connected to 200 volts 50 Hz supply. Okay, the maximum flux density of the core is 1 Webers per meter square. The cross-sectional area of the transformer core in meter square is. Cross-sectional area of the transformer. Here applied voltage of the transformer is almost equal to EMF induced in the primary winding. Okay, if drop is neglected. So that is equal to 4.44 B maximum AN FN1. Okay. So here if not mention anything about the drop, so that's why we can take directly transformer is excited with the rated voltage. So here we required these parameters. Okay, AN is a required. So therefore AN is equal to the applied voltage V1 divided by 4.44 B maximum Fn1, okay, Fn. So now this is equal to V1 is at 200 volts divided by 4.44 the into maximum flux density is equal to 1 Webers per meter square divided by frequency the 50 Hz and number of tons N1 is equal to how many number of the tons? 20 turn. Okay, it is given 20 turn. So now simplify this. What is the answer? .44 into 50 into 20, okay, 200 divided by answer. So this is equal to 0.045 meter square. So now another question based on this concept, answer here. Okay, a 50 Hz 1000 kVA 1200 upon 400 volt single phase transformer has flux density of 1.2 Tesla, induced EMF per turns ratio of 330 volts. Find out net cross sectional area of the transformer core. So we know the equation. We know EMF per turn is equal to E1 by N1. So that is equal to 4.44 B maximum ANF. So we required AN value. So substitute here EMF per turns ratio of the voltage, that is equal to 30 volts. Okay, 30 equal to 4.44. B maximum is equal to 1.22 into AN, frequency the 50 Hz. So now substitute AN is equal to 30 divided by 4.44 into 1.22 multiplied by 50. So now calculate and answer this question. .44 into 1.2 multiplied by 50. Okay, this is equal to 0.1126 meters square. All of it clear? So one more possibility of the question based on this concept. The ratio of primary winding of transformer having 60 number of the turns, the rating of the primary winding of the transformer having 60 number of the turns is 250 volts, 50 Hz. The core cross sectional area of the core is 144 centimeters square. Then the flux density in the core. Okay, so we know EMF induced, that is the applied voltage V1, the directly proportional to here, almost equal to the induced EMF E1. It is equal to 4.44 B maximum ANFN1. Got it? So we required maximum flux density. Okay, so where B maximum is equal to V1 divided by 4.44 ANFN1. Okay, this is equal to 250 volts divided by 4.44 up net cross section 144 centimeters. Then converted into the meters. So here given as Tesla. So that here 144 into 10 to the power of minus 4 multiplied by frequency 50 Hz. Okay, it is multiplied by number of turns is equal to 60 number of the turns. So that this B maximum value is equal to, okay, calculate. Okay, by simplification, this answer nearly equal to 1.3 Tesla. Suppose we have a question, there is one question in the computer exams, that is 100 kVA. If 100 kVA USA made transformer is operated operated in India then maximum permissible kVA rating of kVA rating of transformer would be, so option A 100 kVA and option B 83.3 kVA and option C 50 kVA and option D can't be operated. Okay, like this. Any electrical machine can be operated below its rated value. So your USA frequency, here it is made in the USA. That means the designing frequency of the transformer. Okay, designing frequency. So it is here. So that is made in USA. So that is equal to 60 Hz. Okay, and operating frequency, it is operated in India. Okay, that operating frequency, so in India, so that is equal to 50 Hz. Got it my point? The any electrical machine can be operated below its rated value. Okay, so but it cannot be operated above its rated value. So that means to operate, what is the condition? To operate, so here always operating frequency of the transformer, operating frequency, that should be less than the designing frequency. Okay, designing frequency. So that option D is not correct. So it can be operated below its rated value. So if it is operated, then what will happen? It draws very high amount of the current from the source. So here high amount of magnetizing current from the source, which is undesirable. But that is not our issue. So but what kVA rating can be operated? So is it 100 kVA, less than the 100 kVA? So we know that the kVA rating of the transformer, kVA rating of transformer directly proportional to the frequency of the transformers. Frequency of transformer. Got it? So that you can write here the kVA rating of the transformer in India divided by the kVA rating of the transformer in USA. So it's equal to frequency in India divided by frequency in USA, right? So now substitute here kVA rating of the transformer in India, that is operating volt, the kVA rating. So that is equal to 100 multiplied by 50 divided by the 60 kVA. 100 kVA divided by 50, the divided by 6, that is equal to 83.83 K. So that means this is, you can operate up to, okay, it means that so we can operate, okay, operate it up to, okay, 83.3 kVA only. We cannot operate more than the 83.3 kVA. So this is nothing but maximum permissible kVA rating of the transformer. Okay. So if you have any question, you can ask. This is Unacademy Combat. So play the register as immediately, and this is the Combat at January 12, 2021, 6 p.m. So we have some exciting prizes also. Per rank 1, the 3 months GATE ESE plus subscription. Rank 2 and 3, 1 month GATE ESE plus subscription. from the rank 4 and 500 Amazon vouchers. Okay, so these are the all benefits of it is a competition and access the gate preparation in the 65 minutes, challenging gate questions by the top educators, and super fast fun with the All India Live Learn board. Identify your weakness through detailed video solutions. So this is Evalu per Gate 2022 ECE batch A, which was starts on 21st December. So some of the top educators are taking these batches. The Evalu batch for the Gate 2022 Electrical batch A, which was starts on 21st December. Some of top educators are taking these batches. Please join as immediately. Okay, this is the official Creatrix channel which has 150k plus members. Please join in this group, and it is Unacademy Gate English channel. So please join in this group for any updates from this team. So these are the different type of channels under the Unacademy: Creatrix Gate Electrical, Unacademy Gate Mechanical, Unacademy Gate Civil, Unacademy Gate English, Unacademy Computer Science, Unacademy Gate Questions, Electrical Junction. Thank you. Okay, thank you all. Thank you very much. We will meet once again tomorrow with different concepts. Thank you. Do you want to ask any more questions? You can ask. Otherwise, we will stop the session here.